Greetings everyone. Welcome to a new episode of Mr. Bioinformatics. In 2019, we heard that the Event Horizon telescope captured the first ever image of a black hole. This supermassive black hole located in the galaxy M87. It is 55 million light years away, meaning the light we see today began its journey 55 million years ago. But how big is this black hole? Let me tell you, my dear, that this black hole has a mind-blowing mass that it's about 6.5 billion times that of our sun. Can you imagine, my dear viewer? I hear you now asking, how did scientists capture an image when we usually need light to do that? That's a great question. The speed of light, which is about 299,792 kilometers per second, cannot even escape from a black hole. So how we captured an image? This question reminds me of the poetry that Mr. Bioinformatics once said. My love for you like the light, it is trapped in my heart by the black hole's might. In 1783, an English scientist named John Michell, he wondering, what if there were objects so massive that their gravity could trap light? He called them dark stars. Until 1915, scientists had no way to test this idea. But that year, Albert Einstein changed our understanding of gravity with his General Theory of Relativity. Instead of treating gravity as a simple force, he showed that massive objects actually bend space and time around them. We already covered it in detail in our episode Universe. You can watch it if you are interested about the universe. But just imagine space as a stretchy sheet. If you place a heavy ball on it, the sheet bends, and the smaller objects follow those curves. In 1916, the German scientist Karl Schwarzschild, in his paper Über das Gravitationsfeld eines Massenpunkts nach der Einsteinschen Theory, which means on the gravitational field of a point mass according to Einstein's theory, he asked an important question. What if an object were so dense and compact that it could bend space and time infinitely, creating a region where nothing, not even light, could escape? In this paper, Schwarzschild solved Einstein's equation and showed that space and time could curve so much in certain conditions that would trap everything, even light. This concept led to the idea of what we now call black hole. At first, even Einstein did not believe this could happen. Das ist unmöglich. He thought it was just an interesting idea from the math, not something we could actually observe. In 1930s, Indian physicist Subramanian Chandrasekhar, he began to look closely at the life cycle of massive stars. He asked what happens when a star runs out of its nuclear fuel and can no longer support itself against its own gravity. For smaller stars, this process ends with a relatively gentle collapse to a white dwarf. However, for stars much larger than our sun, the collapse becomes something far more dramatic. As the star's core continues to collapse, the forces at play becomes unstoppable. The pressure and density rise to such extreme levels that something remarkable happens. The core can shrink to a point where gravity becomes infinitely strong, creating what we now call singularity, which is the point of infinite density. Surrounding this singularity is the event horizon, a boundary beyond which nothing can escape, not even light. Once an object crosses this boundary, there is no turning back. Turning back? I go make coffee and come back. But what would happen if I fell into a black hole? Actually, that's impossible. But hypothetically, as you get very close to a black hole, the gravity near it becomes strongly incredible. Gravity does not act equally in all directions. It gets stronger the closer you are to the source of gravity, which is a black hole. So if you were to fall into the black hole, the gravity pulling on your feet would be much stronger than the gravity pulling on your head. This difference in gravitational pull causes your body to stretch out like a piece of spaghetti. Yes, my dear, do not wonder. This stretching effect is known as spaghettification. question. But are there many types of black holes, or it's only one type of black hole? Let me tell you, my dear, that although black holes comes in different types, each with unique properties, they all share the common feature of having an event horizon. However, not all behave the same. There are non-rotating black holes, like the Schwarzschild black hole, which are the simplest form and are characterized by a point of no return beyond, which nothing can escape. But things get more complex with rotating black holes, known as curved black holes. Dr. Mustafa Mahmoud, an Egyptian scientist, described a hypothetical scenario involving a rotating black hole. What would happen if someone passed through it? Let me tell you, my dear, in case you were not crushed, there is only one type of black hole that could allow this, which is a spinning black hole. There is a small chance you might pass through it, but only if you were far from the edge and fall directly into the center. Otherwise, you would be crushed. But in the center, there is no force. So what would happen? You fall down, 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 and then you find yourself in a different sky. Then you fall down into another hole. If you continue in the center and keep going down, you will encounter another sky, and so on. But what if you want to come back? That's impossible. You don't have the power to go back. But hypothetically, if you could return, you would meet yourself because time stops in the black hole. You would meet two versions of yourself. And if you go up a little into another sky, you would find yourself again. Now 3 versions. Then you go up and find your 4th version. Then what? How would your future unfold? There would be no future because there is no time. It drives you to madness, right? One important equation that describes a black hole is the Schwarzschild radius formula. This equation helps us understand the size of the event horizon, which is the point of no return around the black hole. Based on the black hole's mass, the formula is Rg equal to 2gm over c squared, where Rg is the Schwarzschild radius, g is the gravitational constant, m is the mass of the black hole, and c is the speed of light. This equation shows that the size of the event horizon gets bigger and bigger as the black hole's mass increases. For example, if a black hole has 10 times the mass of our sun, its Schwarzschild radius would be about 30 kilometers. This boundary is the point beyond which nothing, not even light, can escape from the black hole's pull. And this brings us to one of the biggest questions. What lies beyond the event horizon? Is it a singularity where all matter is crushed to infinite density, or could it be a gateway to another universe? These mysteries remain unsolved. In the words of theoretical physicist Kip Thorne, whose work inspired the movie Interstellar, exploring black hole is the ultimate quest for understanding the fabric of the cosmos. What drove scientists crazy was how to prove something we can't see. In 1960s, astronomers discovered quasars. What are quasars? Quasars are extremely bright, highly energetic objects located at the center of distant galaxies. They are powered by material falling into supermassive black holes. As gas and dust spiral into these black holes, they get heated to incredibly high temperatures and emit intense radiation, making quasars some of the most luminous objects in the universe. In 1967, Chandrasekhar, he published his book, An Introduction to the Study of Stellar Structure, which he detailed his insights into how stars collapse, showing that massive stars force a more extreme fate than expected. Later, in 1971, the discovery of Cygnus X1, a binary star system emitting the X-rays, provided strong evidence for a stellar mass black hole. Gas from a companion star spiraled into black hole, heating up and emitting X-rays in the process. This allowed scientists to detect the presence of the otherwise invisible objects. These discoveries gave astronomers the first real evidence that black holes might actually exist, even if we can't see directly them. This led the Indian scientist who awarded the Nobel Prize in Physics because his work helped shape modern astrophysics and black holes hole studies. Mr. Mathematics, you didn't tell us if nothing can escape from a black hole. How did we observe them? While we can't see a black hole itself, its presence is revealed by the dramatic effects it has on the surrounding environment. Look, my dear, we know that the black hole have an immense gravitational pull. They attract matter from nearby stars, gas clouds, and even entire galaxies. Basically, anything that comes too close. But instead of falling straight in, this material starts swirling around and forms a superheated disk called a accretion disk. Think of it like water swirling down a drain, except this water is actually gas and dust moving at extreme speeds. As the matter spirals closer to the black hole, it moves faster and faster and reaches extreme high temperatures, millions of degrees. This makes it glow and emit powerful radiation, such as visible light, UV rays, and X-rays. Scientists use powerful telescopes to detect these emissions, allowing them to see black holes indirectly. The more massive the black hole, the stronger its gravitational pull. For decades, black holes were observed only through these indirect effects. However, in 2019, scientists achieved something incredible. They captured the first ever image of a black hole's shadow. How? Scientists used very long baseline interferometry, or VLBI, a technique that connects telescopes across the globe to form a planet-sized super telescope. With this Event Horizon Telescope, or EHT, a worldwide network of telescopes, they captured the first ever image of a black hole. By gathering high-resolution data from multiple locations, scientists reconstructed an image of the black hole's shadow, a dark void that there is no light escape. If you enjoyed this episode, don't forget to like the video and subscribe to our channel. And here we've reached the end of our episode. Thanks for watching. See you next time.